Calculus, video 67, estimating the area under the curve. Okay, so we're going to have some sort of a curve. In this case, I have drawn a function f, which is some curve. And we're going to be looking at the area under that curve. And when we say under that curve, what we really mean is from the curve back to the x-axis. So from the curve back to the x-axis on the interval a to b. So we only want the area of the curve, or under the curve, on this particular interval right here, from A to B. I'll try to draw those straight up and down. We basically want to estimate what is this area in that region there, under the curve, back to the x-axis, on the interval A to B. Now I'm going to erase those lines that I just drew, because the way we're going to estimate the area under the curve is what we're going to do is break up that curve, that area that we just kind of highlighted there, in rectangles. And we use rectangles because finding the area of a rectangle is easy. The area of a rectangle is its base times its height. So we use rectangles because their area is easy to find. And we're going to kind of divide up the area under the curve in rectangles. And in each problem, I will tell you how many rectangles to use. Use 4 rectangles, use 6 rectangles, use 8 rectangles, that sort of a thing. And so, I'm just, for this particular example, I haven't given you what the function is. We're just kind of learning in general the concept here, and then we'll do an actual example in just a minute. But let's say, let's use 4 rectangles. We use the letter N to denote the number of rectangles. N equals number of rectangles. And let's have N equal 4 for this particular example, just to make things easy. So what we're going to do is we're going to divide this space up into 4 rectangles. The problem is that a rectangle, at least the top part of it, because the function is curved, won't actually cover all of that area. And so we'll have a little bit of error, a little bit of part that we'll estimate too much on or not enough on, hence why we have just estimating the area under the curve for right now. All right, so let me draw 4 rectangles. And so let's say here's a middle kind of right here. There'll be one right about here, and another one about right here. I try to make mine equally spaced apart. And then, so what we're saying is we're gonna have 4 rectangles. I'm not gonna draw the full rectangle yet. So 1, 2, 3, they'll have some different heights. But the base, because I want them to all be the same size to make my life easier, I'm going to call that base delta x, the change in the x value. So each rectangle has a base delta x that's the same. In this case, it's a fourth of whatever that distance from A to B is. So if that distance from A to B is 8, for example, let's say A is 2 and B is 10, right? Then each delta x would have a distance of 2 to cover the total distance of 8 from 2 to 10. So the delta x will depend on how many rectangles we have and the length from B to A, the distance from A to B. Okay. The height of the rectangle, remember area of a rectangle is equal to base times height. So the base will be delta x. The height will depend on the method that we use. And right now we have 3 methods. There's more than this, but we'll talk about 3 methods for which height. You could do the left hand. We could get the height of each rectangle based on the left-hand side. We could do the right-hand side, or we could do midpoint. And I'm going to abbreviate that LH for left hand, RH for right hand, and MP for midpoint. So for this particular example, I'm just going to pick one. Let's say we do left hand. And what that means is, for every rectangle, so picture the very first rectangle we have, the height will be determined by the left-handmost point of that rectangle. So the left-handmost point of the rectangle occurs here. And so we're going to get the height based on the function value at that point. The function value at that point would be right here. So that becomes the height of my first rectangle, and it looks like this. So my first rectangle is here, with a base of delta x and a height here. Height given by the function value at that point. Now my second rectangle will again have a base of delta x, and the height from its rectangle will come from that point on its left-hand side. So picture the left-hand side of that second rectangle. The height at that point goes all the way up to whatever the function value is, and then over and down. And I kind of missed there, but you get the point. That is that the height here comes from this point. Again, the left-hand most point on that rectangle. All right, then we'll go here. Third rectangle, left-hand point, all the way to the top, all the way up here, and then over. Now, if you'll notice, in the first two rectangles, we kind of underestimated, right? We kind of missed on, say, this area here and this area here. So we're kind of underestimating. On the third rectangle, we're overestimating. We have too much here. The same thing with the fourth rectangle. We'll take the height on the left-hand most side, let's say from right here. We'll go up to the height at the function value at that point on the left-hand side, go straight over. Fourth rectangle, okay, the height here comes from this point. And I missed this one here. So 4 rectangles, the height of which is determined by the left-hand most point. And what we're going to do is we're going to calculate the area of the rectangles, which isn't hard because it's just base times height. And then we're going to sum those 4 areas of the rectangles together. Okay. Notice on my fourth rectangle, I'm also overestimating here. Okay. That's the idea. That is the estimation of the area under the curve. In this case, I use left-hand side. I'm a little bit underestimating. I'm a little bit overestimating. It's going to come out to be pretty close to the actual area under the curve. What would happen if I were to use the right-hand side as opposed to the left-hand side? Okay, I'm going to try and redraw this exact same thing down below it. It probably won't look exactly the same because it's hard to draw exactly the same. But I have the same sort of function that kind of looks like this. I still want to go from A to B, kind of the same interval here. But let's use right hand. So this first one is left hand, and this one is right hand. Now, still want to do 4 rectangles, so I'm going to divide this up into 4 rectangles. All right, looks like 4 rectangles. Again, delta x for the width of each rectangle. But this time, the height will be determined by the right-hand most endpoint, the right-hand most point of every rectangle. So in my first rectangle, that's this point over here. So the height will be here, determined by the right-hand side. In second rectangle, again, on the right-hand side, the height will be here. Third rectangle, right-hand side, the height would be here. And fourth rectangle, right-hand side, the height would be here. Okay, that would be the right-hand method. The midpoint method would be you take the midpoint of every rectangle and determine the height based on that. Now, let me go back to my right-hand side. Now I've overestimated in my first one, under in my second one, under in my third, and underestimated in my fourth. So, probably because my picture is a little bit off, but I'll have probably a little bit more of an underestimation for this one. The midpoint, similar idea. All right, function, try to draw the same from A to B. Again, 4 rectangles. Each rectangle having a width of delta x. The height, though, will be now determined by the midpoint of each rectangle. And so I will go up from that point, and from that point I get the height of the rectangle. Again, midpoint of the second rectangle, go up, the function value at that point gives me the height of that particular rectangle. And typically, the midpoint is a better approximation than either the left-hand side or the right-hand side, because it's in the middle of the rectangle. And often on the midpoint, what you're doing is you're getting a little bit of not enough on one side of the rectangle and too much on the other. For example, on this first rectangle, I'm overestimating here, but I'm underestimating here. And so it kind of cancels out. On the second rectangle, I'm overestimating here and maybe pretty accurate there. The third rectangle, I'm underestimating here, but overestimating here, so it kind of cancels out. Same idea, fourth rectangle, I'm underestimating here in the pink and overestimating here. And so the midpoint ends up being probably the most accurate of all 3 methods. This is the midpoint method. But it turns out, I don't care which method you use. Left hand, right hand, midpoint. Actually, depending on the problems I give you, I will probably specify. Use left hand, use right hand, use midpoint. Or have you do all 3, or 2 of the 3. But let's not get too far into the weeds here and forget the overarching goal. We won't reach our overarching goal today in this particular video, but I don't want to lose sight of it as we start to calculate the estimated area under the curve. Okay? Because I don't really, in the end, when this is all said and done, I don't want to estimate the area under the curve. I want the exact area under the curve. That is our goal. Our goal is not the estimation. Our goal is to find the exact area under the curve. Let's not lose sight of our goal. Okay. So I'm going to spend a little bit of time talking about how do we get to the exact area under the curve, understand that, and then go back to doing a problem of an actual example of estimating the area under the curve. But I think it helps our understanding of estimating the area under the curve if we first understand how do we get the exact area under the curve. Okay, so how do we get the exact area under the curve? And why don't I care whether you use right hand, left hand, or midpoint? Let me go back to our very first one here, the left hand. And I don't know, maybe I can copy and paste it down below. Let's see if it'll let me. Okay, not bad. Okay, so we have the same picture as above. Let's talk about how can we make this, using left hand, how can we make this more accurate? How can we have less of that pink shaded error region where I'm underestimating or overestimating? And the answer is, the way we become more accurate is by having more rectangles. So, more rectangles equals more accurate. More rectangles, more accurate. And you can see that if I add some rectangles here. So we have our 4 rectangles. What if n is 8? What if the number of rectangles is 8 now as opposed to 4? Look what happens. I will get, let me erase a little bit of this here. Okay. Now instead of 4 rectangles, I'm going to get an extra rectangle in between each one. So the first rectangle is still going to have a height here, but the next one is going to come up and have a height here. Notice what just happened. I almost wish I wouldn't have erased it. When it was just one rectangle there, the pink was all of this right here, right? That was my error. But now that it's 2 rectangles, I've reduced it to just this and this. I've reduced the amount of error that I have. Okay. Same idea on this next one. Remember, I had this one rectangle here, and the error was all of this. But if I make that into 2 rectangles, I'll draw a line up to here, and then I'll come with a height over from that part. And notice that the second part of this reduces the amount of error that I have. I'll have this one, but I won't have this error there. I'll only have this part. More rectangles, less error. Same idea as we keep going here. I'll have this other rectangle who will have a height here, and then the next one will have a height here. Still an overestimation, but less of an overestimation than before. Same thing here in this last one. Still an overestimation, but less than before. We are more accurate here. We have less pink space here than we had before. But notice what happens to our delta x's. Okay, it's still delta x's. They're all still delta x's, but they are smaller than they were before, because I have the same space from A to B, the same length, right, the same distance from A to B, but now I have 8 rectangles as opposed to 4 rectangles. That's more accurate. More rectangles, more accurate. How do I become even more accurate? More rectangles. 16 rectangles, 32 rectangles, 64 rectangles. Right? They get too small for me to even really be able to draw this. But the more rectangles I have, the more accurate this becomes. Right? If I were to draw this again with lots and lots of rectangles, I'll give it my best shot. Good. Let's try lots and lots of rectangles. Let's have say a little one here and here. And what you're seeing is the more rectangles I have, the less error we have. Still have a little bit of error, but it is a lot less. So probably can't even really draw like the pink area here, but we have less error. More rectangles, less error. But now what happens to my delta x's? Right? Now I don't even know how many I drew here. I drew a lot of little rectangles here. But my delta x's are becoming smaller and smaller. Each of these represents a delta x. I can't even draw them all in there. So the way we become more accurate is have more and more rectangles. Delta x's become, the width of each rectangle becomes smaller and smaller. How do I get the exact area under the curve? That is our question. That's what we're trying to get to. We're going to go through this approximation of area under the curve in our ultimate goal of getting the exact area under the curve. So don't get too lost in the approximation and lose this big goal. All right, that's our point. How do we do this? By letting the number, so question, answer, letting the number of rectangles go to infinity. We're going to let the number of rectangles go to infinity. That's how we're going to get an exact area under the curve. We're going to have a limit to infinity of the number of rectangles. What does that do to delta x? If the number of rectangles goes to infinity, what happens to your delta x? We've already seen that it's the more rectangles we get, the smaller delta x becomes. What we're going to find is the width of each rectangle, delta x being the width of each rectangle, try writing nicer, the width of each rectangle, delta x, gets smaller and smaller, and that goes to 0 when we let the number of rectangles go to infinity. So n will go to infinity. That forces delta x to go to 0. That will give us an exact area under the curve. And that is the reason that I don't care whether you use left hand or right hand or midpoint. Picture what's happening here. As the rectangles are getting more and more and more, they're becoming a smaller and smaller width. And what's happening is the left hand, let's pick this rectangle here, the left hand and the right hand, doesn't really matter eventually which one I calculate the height from, because they're being pushed closer and closer together. So as delta x goes to 0, the left hand and the right hand basically get squished together. And so whether you're using left hand or right hand or midpoint, it doesn't end up mattering, if that's a word, because those points are coming closer and closer together. So while left hand, right hand, midpoint, you'll get very different answers if you're only using 4 rectangles. You'll get the exact same answer if you let the number of rectangles go to infinity. So it's probably a long enough video as it is. I'll stop this video, and then in the next video we'll do an actual example where we estimate the area under the curve. That will lead us into not just finding the estimated area under the curve, which we care about, but that's not the main goal. We're going to take that area under the curve and using a pattern here, write that in the sum notation, that sigma notation. From there, go into Riemann sums. And that's eventually how we're going to come around to finding out how do you calculate the area under the curve exactly, which will come from what we call the fundamental theorem of calculus.